All right, 11 minutes late. Okay, any questions from anything?
How can you size a starting circuit?
How can you what?
Size a starting circuit, because like when one of the
Starting circuit?
Yes.
I don't know what that means.
Yeah,
The startup
the
circuit?
startup circuit.
Oh,
Yeah, like the only thing I can figure out is just just become an LT spice, trial and error.
no, you have a weak transistor you need to shut off. There's lots of different designs that'll work, but you want to minimize the power. So there's an infinite number of solutions, but in the side that has the low power, you don't want, here, I'll real quickly, you can have your BMR here, and then here's your transistor. Yeah, this is one. Then here would be your switch, and this goes to the BMR. Right? So what happens when this is off? I hate it when things don't work. If I ever sell my house, you want to buy it because everything in my house works. I don't have anything broken. Nothing. All right. No stains, no bad paint, nothing. Anyway. So what's V bias? Do I have to draw the beta multiplier? What's V bias when it's not started up?
0.
0. So how much current flows here?
0.
And then what's this voltage?
VDD.
And what happens to this transistor?
On.
And it leaks the current until this starts up, right? Everybody follow that? And then what happens next? See, another thing that's different is this right here. I don't know what that is. Teach me if you know what's going on. This thing just appeared too, and now I can't move it. Yeah, whatever. Yeah, all right. So this goes out, and the current, it starts up, and then this goes up to V bias, right? So then I get a current through here that's not equal to 0, right? So what I want this is long L so that the voltage drop across it, this goes towards ground. Now keep in mind, this is at a VGS where it's connected over into the transistor. Like this. So this is at a VGS. So even if it doesn't go to ground, this could have a negative VGS. So if this was at 1 volt and this was at 0.8 volts, then this VGS would be minus 0.2 volts. Everybody follow that? Yeah, and it's off more. So you just need this to be long enough L. What's another thing you could do if you don't like this? What could you also modify this to do? No one's playing with their phone, right?
Well, like, because I tried that, and I had to play with the lengths.
You make the length long. There's no playing. Just pick a long length. Boom, done. And then you could also do this. If you want to have two threshold voltage drops, and then you don't need us because you have an extra threshold. So you can make this a long L and this a long L, but smaller long L's because you have the threshold.
Is there a problem with making the bottom one diode connected as well?
This one?
Yes.
Yeah.
There's a problem.
This is the current source. You want this, I mean, you can set the current in here, but then the problem is if you make this diode connected, you don't have control on the current as well as if you bring it over from the BMR. So you can get it to work. It'll just, if it get too high a VDD, then the string can turn on. You can get a lot of current flowing. This voltage will go too high. So, all right, we ready to talk about common source amplifiers? All right. How were the pre-taped lectures? Better than the live lectures. We should have pre-taped all the time.
How's the lawsuit going?
It's over.
Who won?
All right. So common source amplifier with current source load. And I'm going to be able to tell you if you are following what's going on I'm going to be able to tell if you're following by asking questions. And so I have the following. Here's the bias, and then that comes down here. And then I'm going to connect this. I'm going to make it real simple just to begin with. I'm going to put this transistor here, and I'm not going to use my bias circuit. I'm just going to do the following. And so what does this form? Current mirror. But there's no way for me to force the current in this transistor to be precisely equal to the current in this transistor. So the way I'm going to do that with the setup here is I'm going to put a big resistor here. And I'm going to put a big capacitor here. And I'm going to put a voltage source V in here. And I'm going to call this V out. And then I'm going to write the DC voltages. How was having a practice test?
Oh, was awesome.
You don't want that with the final, right?
What? Yeah.
Oh, so much work.
Oh, I see.
Yeah, it's easy for you guys. Just download it. Isn't this nice? All right, so I'm going to call this voltage VSG. I'm assuming all the same sizes for the PMOS, all the same size for the NMOS since there's only one. And I'll call this current as I. And I'm going to ask you some simple questions. What's this voltage? Okay. What's this voltage? Looking good? What's this voltage? What's this voltage? What's the DC value here? This current's I. What's this current?
Should be I.
How much current flows in this one?
Very little.
That's the DC. Any questions about that? Okay, I got a question. Explain in simple terms why I put the big resistor between the gate and the drain of the NMOS.
Because you don't want the current to be split. You want most of the current to go through the transistor.
You can't have dueling current sources. There's no way to make the currents precisely equal, right? And so the way I'm doing it is I'm diode connecting this so that whatever current flows down, this is diode connected, this will sync and adjust to the correct DC value. Now, one of the problems is when you look at the transient simulation, if you have a big resistor like a gigaohm and you have a big capacitor like a farad, that's a billion-second time constant, and so you'll oftentimes have to set the initial condition here in a transient so that it biases up correctly, because there's no way to charge this node to the correct value. In a real circuit, it's fine, but in a simulation, you have to wait forever. Everybody follow that? Not always. Sometimes they'll do an initial operating point calculation and give you the right value, but if it doesn't, then you got to set it. It's a diode-connected MOSFET for the purposes of DC biasing. But now for AC, I'm not going to get any AC current through there because this is going to be a big capacitor that I would have to charge and discharge. And load, when I say big, it's big compared to the output resistance of the two MOSFETs. So big meaning that when I calculate the AC gain, it doesn't load the AC gain. All right, so let's do, any questions on the DC? I'm going to do an example after this, and then we'll go through. Actually, I'll do one different than the homework problems. Everybody saw our homework? Were you checking it the whole weekend? He's gonna be evil and make something due on Wednesday.
I don't know, but the project's up.
Projects are up? Yep, and it's way over a month to do the projects, or it's over a month. So they're due in May, and it's March. But I guarantee someone's going, can we have the projects earlier? Oh, brother. Like you could do them any earlier, right? Yeah. All right. I get that every time. We need the projects earlier. Come on. It's like standard complaint. All right, let's do the AC. So this was the DC. And that project's a little bit challenging because you've got to operate at low voltages and be able to drive big loads. And make sure you understand how to do the project, not just messing around, so you can actually describe it when you go for an interview. What's your project? I don't know. Don't do that, all right? That's bad news. Unless you're not going to do a circuits job. I'm going to do MATLAB or something like that, then that's fine, okay? All right, so let's do the AC part. What's the AC voltage here? Why? What's the AC here? What's the AC here? What's this AC voltage? Okay, what's the AC current flowing through here? Think about it, it's easy. Well, it's not GM because what is the AC? It's going to be, what's this AC voltage? Let's do that one. What's this AC voltage? You're going to laugh at yourself when I tell you. What's this current? AC current, 0 minus V out over R out P, or minus V out over R out P. Did I make that hard? You make everything hard. Okay, so what's this current? We'll call IN. It's going to be two parts, right? It's going to be GM times VN plus because remember, this transistor looks like this. And what's the VGS here equal to? And that's in parallel with R out N, and that's the total ID that flows. Everybody follow that? R out N is the output resistance of the NMOS. I hate it when things magically stop. Don't like magic. Why did I not include the current source up here? I just said it's R out P. Here? Yeah, VSG is 0, right? It's good, man.
That's what it feels like.
If you ever go get a massage, please tell me. I can have my voice. Oh, all right. So, yeah. So tell me, how do I find or how do I relate all that stuff? What's going into the node? And what's going out? So I'm going to do this problem again in a second, but I'm going to take this equation and write it on the next page nice and clear. Okay, so that's minus V out over R out P is equal to GM V in plus V out over R out N. Looking good? All right. Passion's good. Difference good.
Previous circuits, we didn't have to add that extra.
What?
Extra one. Previous circuits, when we used GM, the ID was just equal to GM times.
Yeah, because we were assuming that R out was much, much greater than 1 over GM.
Okay.
We can do one that way if you want.
No,
But let's continue. All right, solve for V out over V in. And I want you to, because there's a reason I'm going to do it this way. So if I move this out, would everybody agree that's minus V out times 1 over R out P plus 1 over R out N, and that's equal to GM V in? Or V out over V in is equal to minus GM times 1 over R out N plus 1 over R out P, or minus GM times, what is 1 over R plus 1 over R like this? What is that? It's the parallel, yeah, it's the parallel combination. And there's my gain. Anybody agree with that? Let's do this problem a couple more ways. Everybody cool with that? That's the gain for a common source amplifier.
And it's a common source because the input's in the gate.
Yep,
Yeah,
let's
so-
do that. Let's make sure we follow that. So here's my circuit. Here's my amp. Here's my V in. Here's my V out. I look and I've got plus minus, plus minus. Here's V in, here's V out. So see, the source is common with the input and the output. Any questions? Let's do it again. Let's change colors because this color is no good. I'm only going to do the AC part. Let's see. So I'm going to sketch the output resistances of the transistors. External to the transistors. So what is the VSG of this transistor? And what's the VGS of this one? So what's this current here?
GM times VN plus.
No, just GMVN because I put the R out here. Now, wouldn't you agree these are both in parallel? So that'd be R out P in parallel, and that the currents are flowing backwards through them. In other words, they're flowing like this. Everybody agree with that? So couldn't I write V out equals R out N in parallel with R out P times minus GM V in? Or V out over V in equals minus GM times R out N in parallel with R out P. Isn't that the exact same result? Okay, so I'm going to show you one more way, and then we're going to do a numerical example with simulations. One other way of writing the gain of a common source is the resistance in the drain divided by the resistance in the source. Now I'm going to do this in my numerical example. I'm going to do this a couple ways. So the resistance in the drain is the following. Let's minus this. It would be minus R out N in parallel with R out P. And the resistance in the source would be the resistance I see looking up into the source, which is 1 over GM N. Would everybody agree those are the same? So that's a quick way. When I go through transistor circuits, that's how I analyze them. I don't do math. I just go gain from here to here is this, gain from here to here is this by using that equation. Now I want to prove to you that the resistance in the source is 1 over GM. Looking into the source. And so I'm going to ask you, how do I determine that, or how do I prove that? The way I'm going to do it is I'm going to put a test voltage in there, and I'm going to look at what the current that flows is. All right? So here we got the following. I'm just going to do the transistor by itself. I'll ground this. I'll ground this. Of course, it has to be biased up. I'll call this V test. I'll say this is I test. I'm going to neglect the output resistance, because I already drew that external. And I'm going to say R into source equals V test over I test. All right, so what's the AC voltage there? 0. What's the AC voltage there? So what is VGS? Anybody agree with that? Any questions? And I've got a current flowing down here, ID. How are ID and IT related?
Negative I T.
Right on. So can I write ID as GM VGS? Everybody agree with that? Would I be able to write that as GM times minus V test?
Yep.
Or just looking at this part alone, V test over I test equals 1 over GM. And this is the resistance into the source. Looking. See, I should turn the or the whatever that camera is called on the laptop. All right, let's do one more real quick before I do my numerical example, real fast. If I have the following, or let me ask this first. If I have this, we'll see how well you learned. And I ask, assuming it's all biased, what's the resistance looking in there?
R N plus RS.
What is it?
RON plus RS.
How about R out N times GM? What is it precisely? Let's do it precise. No. You guys watch my videos, right? What is, well, if I have a resistance here, what is it just in the generic case? If I have like a cascode like this, we drive this before I left. What was that resistance?
GM squared.
R out plus R out times 1 plus GM R out, or approximately GM R out squared. You agree with that or not? Okay, so if I have a resistance here, and I ask what's the resistance looking in there, what is it approximately?
R out plus R out times 1
R
plus-
out plus GM R out RS, right? And if RS is big, then this can be approximately GM R out RS. Or GM R out squared if RS equals R out. Any questions on that?
GMR out constant.
This thing?
Yeah, it's not R out squared because it's R.
If this was R out, it would be R out squared, right?
Yeah.
Questions? Proceed or not? Because there's a reason I'm going over this. Let's go back to our common source. There's a reason I go over everything, I guess. Let's go back to our common source amplifier and look at the following. And ask if this is V in, what is V out over V in? Look at the gain quickly and tell me using the resistance in the drain divided by the resistance in the source.
GM.
What's the resistance in the drain?
It's negative. So it's negative GM.
Resistance in the drain is what? R out P in parallel with what's here, right?
Parallel with
But if this is big, if RS is reasonably sized, then this is going to be much larger than the output resistance of this. Or divided by 1 over GM N plus RS. Resistance in the source is the resistance I see looking into the source plus RS. Now I'm going to do examples and we're going to prove if these are right or wrong. Before I do, any questions? Can you prove this?
We don't have to worry about calculating
The resistance looking into the drain?
Right.
You can add that. It would just be in parallel with GM R out RS, or 1 plus GM R out RS. So we can put that in there, but calculations start to get crazy. Let me prove this. So this is R out P, right? Assuming that's small compared to the resistance looking in here, the current that flows is ID, and that flows through here. V in is VGS plus RS times ID. So I can write V out equals minus ID times R out P. Looking good? And that is V in is VGS plus ID times RS. Correct? Am I losing anybody? If I have a quiz on this on Wednesday, everybody's going to get it right, right? Okay, so I'm going to replace VGS with something having an ID. What do I replace VGS with? G. And then the IDs cancel, and then this and this are equal. Yay or nay? We ready for a numerical example? So I'm going to do it without a resistance in the source, then we'll do one with a resistance in the source. When's your next homework assignment due?
next Monday.
Is that a bummer?
Yeah.
You miss him? Liar. How come you're not falling asleep today, Andrew? I had a good spring break.
really did.
That's good. All right. All right, here's what I'm gonna do. And what was the typical output resistance for one of the MOSFETs with the long channel process? 5 meg? All right, so we're going to make them have a resistance of, how about a gig? Make it much bigger. And I'm going to make this also 40 by 2. Have everything 40 by 2. And I want you to find V out over V in. I'm going to assume the same lambdas in the book for the other biasing. 0.01 and 0.02, or what were they?
0.0125.
So one is a lambda 0.01 and the other is 0.0125. Yep. All right, tell me what to do.
Find VSG.
Why? Why do I need to find VSG?
Oh, because you need to calculate the amps when you eventually find out VSG.
How about let's not find VSG and just say this is 10 microamps
Sure.
and this is 10 microamps. Would everybody agree with that?
Yeah.
Then would everybody agree that I could write the output resistance R out P is 1 over 10 microamps times 0.0125, and R out N is equal to 1 over 10 microamps times 0.01. Is that what they were? I've already forgotten. All right. And then GM is equal to what? Square root of 2 times all right, do I need to get my calculator out, or can somebody tell me what these are equal to? I ask and then I'm like, which, what? This one's 219? I use nice numbers. Now, before I do the AC, I'm going to verify those. I want to see how close I am. How do I do that? How do I do that in LT Spice? How do I find R out P, R out N, and GM? Yeah, error log with a .op. I don't want to waste time if I did something wrong with my calculations. So I'm taking a mental picture of that. And then I'm going to go over here. Oops, I forgot to upload that. I better do that. This is lecture 14. And then let's go, before I do anything more, and this is 40 by 2. And let's get out the scissors. Goodbye. Goodbye. And then let's grab a PMOS. No? And then because it puts the source on the bottom, we'll Control R it twice and Control E it. So it likes, if you look at the net list, that means that's source, gate, drain. So that's how you identify which one is the source. It shouldn't matter, but if you look at the net list, you want to make sure it's consistent with what your understanding is. And then let's right click on this, change this to P_1U, change the length to 2U, the width to 40. Has anybody put 2 and 40 or something like that in there? Like 2 meters and 40 meters and not realize what's going on with my circuit. All right, press Control and right click and then double click on that, show it. And then come over here. What? Yeah, but the problem is your leakage current's 1,000,000 times more and your capacitances are 1,000,000 or 1,000,000,000 times or whatever, 10 to the 12th, times more, etc. You get funny business. Funny business ain't good. I don't know, unless you're into funny business, then it's great. It's funny. Okay. Favorite time in my class is drafting. All right, let's call this, let's put a cap down here. And let's stretch that over. And right click there and call it 1U. And then get a resistor.
One micro, generally big enough for?
And let's put 1 farad. How's that?
No, not a debate. I'm actually asking if 1 micro is generally speaking big enough.
Well, it's a time constant of 1,000,000th times 1,000,000,000th, so it's 1,000-second time constant. You know, I'm setting myself up for a learning experience in a moment. I hope some people realize that. Because there's people in here that haven't had 6,000 lectures in LT Spice, and so I want to make sure they don't feel pain. All right, so let's make this advanced AC. Yeah, let's put a sine wave in. 0 amplitude, 1 millivolt frequency, 1 kilohertz. Yeah, that's good. All right, and then last but not least, let's do this. And since we want to have pretty schematics, let's come up here and say V out and then port type output. Okay, plop that down. Aesthetically pleasing. Are there any issues other than, oh, we need to do one other thing. Dot include CMOS edu underscore models dot text. Text good. All right, say.
You also have to do that zero thing.
Plot options, plot win size. Yeah, that one's pretty important. I was noticing that I had some of them this morning when I was doing the homework, that it didn't work without this in here. This program was initially for switching power supply, so it has an algorithm where it throws points away when it's plotting stuff and saving stuff so that you don't have files that are too big. And so what it does is forces you to not throw away as many points, and so you don't get ridiculous looking waveforms, because it thinks it's smart and it throws away stuff you actually care about. So on this Pro, you understand, if people that have had 421, 621, You see here where it gets everything, right? And you notice in 421, 621, when you use Cadence, commercial software, it doesn't. You have to actually tell it what you want. If you don't say, I want this, it won't save it, because if you're doing a billion transistor circuit, it's just not reasonable to save everything. So it simulates and then saves what you want, and then that's it. And then I'm going to poke the running man and do a .op. And then look at the currents, and they look pretty consistent at 10 micro. IB is the gate current, I think, or the bolt current, 10 micro, 10 micro. And then I'm going to go up to and someone have their calculator handy, SPICE error log, and look at M1's GDS. So M1 is GDS is... So that looks like it's roughly 5 meg if I do 1 over 0.2 micro. And we calculated 8 meg. Everybody see that? And this one, which is M2, oh, it's about 5 meg as well. So we're going to have a little bit lower gains than what we calculated using our hand calculations. Any questions about that? Everybody sees we calculate 8 and 10. And so we're going to get, when you put those in parallel, like 4 meg, I don't know what it is, something like that, 3.5 something. When we have 5 and 5, what is it going to be? 2.5. And so there, we're going to have a lower gain just because of that. Now, I can mess around with the output resistances by changing the DC, but that's, you don't want to waste time on that. I mean, they change, and you're trying to estimate. Now, the other big one was GM, and it's GM for, ooh, that one's really close, 212 micro, and we calculated 219 micro. So our gain's going to be a little bit lower than what we hand calculate when we simulate. Any questions about that? Well, remember, one big thing is the drain to source voltage. If you change the drain to source voltage, it's going to change R out, can be a factor of 4. Okay? So now let's calculate the gain. And the gain is GM times R out N in parallel with R out P, or 219 micro times 8 meg in parallel with 10 meg. That'd be 80 over 18, which is 5, right? What is 8 times? That's 80 over 8. What is it? 4.4? All right, so what's 219 times 4.4? That seems large. $964? That's big. All right, that's our gain. Now we're going to simulate that. Any questions? Everybody see what we're doing, because that's what your homework on Monday is about, is doing gain calculations for PMOS and NMOS. Any questions about this before I sim it?
You determined to use that equation why specifically? Because like we keep running.
No, this is what we derive 3 or 4 times at the beginning.
They're all the same.
Yeah, it's just the same thing. I derived it like 3 or 4 different ways.
Okay.
I can derive it, rederive it again. I mean, it takes me 2 seconds. I just figured, why should I? I mean, come on. All right, so we got 964. Now I'm gonna go over here and I'm gonna hit save. Then I'm gonna do fit. And I'm gonna do move. I'm gonna do boom. And I'm gonna do boom, save. File, save as, and then we'll do lecture 14, example 2. And then I'm going to go back to this, and I'm going to plot 3 or 5 cycles. Now I'm concerned about a lot of things. I have a mistake here we'll talk about in a moment. But I'm concerned that this voltage won't be steady state. So if you look at it, you see what the voltage is when I did the dot OP? You see it was 876.14 millivolts down in the lower left corner. That's the DC point I want my transient to start at. The concern is, and this is why I don't do this in circuits I actually build, the big resistor with the 1 gig and the 1 farad capacitor is a time constant of 1 billion seconds. Okay, so when I hit run now, first thing I'm going to look at is I'm going to look at this voltage and see if it's about 8 point whatever. Oh, it is. It powered up right. Okay, then I'm going to look at this voltage and make sure it's right. And there it is. But if I look at the two, they should be the same, but offset by a DC, right? So I'm going to go here. Everybody follows. They should be the same AC voltage, but this one should obviously be at a VGS, and this one is swinging around ground. So I'm going to go right-click, add a plot plane, and pull this node up, and I say, hey, this node's not swinging. Why isn't this node? I got a 1 farad capacitor. What's the deal? Let's look in the book. Oops, what just happened?
It's Monday.
How do I projector restore image? What?
That's your.
No source detected? Yeah, whatever. All right, let's go to the end of chapter 1. My computer's feeling neglected, and so it's treating me bad today.
Oh.
Look at number 3 here.
Oh.
See what I did?
Oh, it's too small.
Yeah, it's not 1 farad, it's 1 femtofarad. It's basically nothing. So I'm going to go ahead. I thought people saw that when I made the mistake and you weren't saying anything. So I make it 1 farad, which is 1. Now let's rerun the sim and see what happens. Hey!
If you put 1 MF, is that a millifarad or will
Yeah.
it screw it up?
No, it's 1 millifarad, and MEG is meg.
So if you put something in front of the F, it'll use
Yeah,
the. Okay.
yeah. All right, everybody follow this? Now my signal's coming through here, and it's going up from 7.5, roughly 0.2. It's 1 millivolt. Okay? It's 2 millivolts peak to peak, 1 millivolt peak. Okay, any questions on that? And now I'm going to go over to my output, and I'm going to show that. And look, my gain is so high that the output's clipping. So if I put 1 millivolt in, the gain is 1,000 roughly, or 964 we calculated. That means I should get 1 volt out for 1 millivolt. So what am I going to do? Wait, let me ask a better question. What was the DC voltage right here? 876 millivolts. So how low can this go before this transistor starts to triode? 0.76 millivolts, right? Because the threshold's 0.8.
So that's why it's clipped.
Yeah, it's clipped. So I'm gonna go over here and I'm gonna put this at 0.1. Then I'm gonna hit run again, and then I'm gonna see that, hey, it's got a gain of 100 and I can actually see it. Any questions on this before I tell you how to find the gain? Everybody see what we're doing. Everybody follow, the DC voltages are different. Now I'm calculating the AC gain. Okay, so now I look and I go, okay, well, my peak input's 100 microvolts. I'm swinging around 0.87, and I'm going up to roughly 100 or 1 volt or 130 millivolts. Everybody follow that? So my input's 0.1 millivolt, and my output's 130 millivolts. So what's the gain I'm seeing? Roughly.
130 millivolts divided by.
Yeah, 130 millivolts over 0.1 millivolts, or 1,300. Who follows that? This goes up 0.1 millivolts. This goes up 130. It's a little less than that. Let's say 120. So the gain would be 120 divided by 0.1. 1,200. Any questions? Yes?
Why is it so large?
Good question. I don't know. Maybe it's changing when the voltages change, the output resistance is going up because the voltage here is changing across the device. So my guess would be R out is also changing, and that causes the gain to go up. I've got a question. So I've got V out, and actually let's plot this one just to make it easier. Let's do this.
You show what happened if you remove the 1 gig resistor?
It won't bias up. You can try that on your own. There's no way for this to sink the proper amount of current. So let's go here, and then let's select this waveform and go here. And there's V in and there's V out. How do I know the gain is negative, like I calculated?
It's opposite.
Yeah, when this one's going up, this one's going down. When this one's going up, this one's going down. Okay? When I put my gain, I put V out over V in. Can I do that here with this simulation? No, why? Yeah, because whenever V in goes to 0, I'm going to be dividing something by 0. So here's what I'm going to do. I'm going to save this sim before I do any questions on this one. All right, let's close this. Let's go back, let's pull it up, and then I'm going to do a file, save as, example 3. And then I'm going to change this to an AC of 1. And I use 1 even though I know it'll clip because I'm lazy, because then V out over V in is always just V out, because V in is 1. Now remember, with AC, it assumes you're smart. It assumes the user is smart enough to know that it's going to replace everything with small signal model. So even if I put 1,000,000 volts in, it's not going to know. Okay, so I hit 1. I'm not going to show any of this stuff. And I have 0. I can put 0 here. Hit OK. And I've got my nice little source here. I'm going to right click here and go to frequency or AC analysis. Do a decade sweep, 100 points per decade. Start at how about 10 hertz and go out to how about 10 kilohertz. Then I hit run. First thing I'm going to plot is V in. What do you think is going to happen when I hit V in? What is V in? 1 volt peak, but what is it going to plot? 0 dB. 20 log of 1. Let's find out. Right. Any questions? And our gain was 1,200. Let me pull up the old calculator. Let's see, that will be 1,200 log times 20 equals 61.5 dB, which we could have guessed 1,000 is 60 dB. So when we plot the output, that's weird. I don't know why it seems lower here. Maybe I'm reading that plot previously wrong and it's less than 100 millivolts. This is showing, let's see, it's a gain of 500, which actually makes way more sense. So how do I show, does anybody not follow this? No, you don't follow? So this is blue as V out. and it's 54 dB, which if I right click here, I can put it in linear and show it as 538, or I can go back to dB. So, Clayton, why do we use dB? Good question.
Makes the math easier.
No, what's the answer? Why do we use logarithm and why do we use dB? It's a real simple answer. I heard so many answers, I don't know, I'm sure all of them are right. My answer is, the simple one that everybody uses is because you can use big things and small things together. So if I go back and I show, oh, well, what is V in? And I plot that on the same plot. There's my V in, which is 1, 1, and here's my 503. I can plot them really well on the same plot. Even if the gain was higher, I could still plot them on the same plot. And I can plot low frequencies and higher frequencies on the same plot. So dB, logarithms, it's always the same thing. Small things and big things together on the same plot. All right, so
It makes the math easier.
what's that?
It does.
Well, because I put 1 volt in. So here, let me show you. Let's make sure we understand that. So let's get rid of this, and then let's put here, divide by V of V in, and plot, and it's exactly the same. Now, if I hit save, and I go back here, and I put what I had before, which was 0.1 milli, and I go OK, and I save it, and I run it. Looks exactly the same because I'm plotting a ratio, right? But now look at what happens if I plot my input. It's no longer 1 or 0 dB. It's minus 80 dB because it's 0.1 millivolts, or 10 to the minus 4 times 20 log. And then my output is now at minus 25 dB. Remember, I put 1 in because I'm lazy and I don't want to show the ratio, so I just plot the output. One of my trick questions, not trick, one of the questions I put on in circuits is I say, hey, what if the input's 0.2 volts? Then you can't use 1 and you have to plot V out over V in. Okay, any questions on this example? Yes?
So there's no current going through the 1 gig resistor?
Let's find out. Let's go right click and put this at linear because you don't know what minus 200 dB is. Picoamps, small compared to, that's 1,000,000 times smaller than the microamps. All right, let's do one more thing and then we'll call it a day. Any questions on any of this? Yes? No, that's what I was saying. If I go back, no, I didn't. It was 1,300. I said when I did the estimate here, I probably didn't measure it right. So let's do that real quick just so you can see. So I put 0.87. And so if I take this V out and I subtract 0.87 and I go, I don't know, it looks pretty close to maybe 110. I mean 1.1K. I don't know why the transient simulation. Maybe it's the simulator's wrong.
Yeah, simulation. Bro.
Let's send the author, I think your simulator's wrong.
Doesn't work, you still I'm always right.
Yep. Well, one thing that could be an issue is the, yeah, I don't think that's an issue. I was going to say the AC coupling in, but with 1 farad, that's huge. All right, let's do one more thing real quick. Let's take this same circuit and add a resistor and source, in the source of the NMOS. And so I'm going to do the exact same thing. And I'm going to make this a little bit one-sided, that my resistor dominates. So this is 40 by 2. 40 by 2. And I'm going to make this 10K. Yeah, it's not that much bigger. And then I'm going to put my capacitor here, my V in. And I'm going to put my big resistor there. And I'm going to call this V out. I'm going to go 40 by 2. And then I'm going to ask you, okay, what do I have to do different here? Is it going to bias up correctly? What's the current flowing in this device? And what's the current flowing in this one? And what's the current flowing in here? So wouldn't everybody be okay if I wrote on here in orange, R out P equal 8 meg, R out N equal 10 meg, GM equal to 19 microamps per volt. Is everybody okay with leaving it like that? So now, I've got the 10K here with the GM and the R out. I'm saying that I'm going to neglect the resistance looking down in here and just say that the current flows through this 8 meg alone because of that resistor. So I'm going to say V out equals minus ID times R out P. Anybody agree with that? Then I'm going to go over and I'm going to say that this VGS plus this ID times 10K is V in. Which is also equal to ID over GM plus ID times 10K. Then I can write V out over V in equals minus ID times R out P all over ID times 1 over GM plus 10K. Any questions about that? Or this is equal to minus 8 meg all over 15K, roughly. Because what's 1 over GM here? One over 200 micro is roughly 5K. Any questions about that? Anybody follow that? So then I'm going to come back and say, all right, well, what's the gain going to be? Get my calculator out here. And then I'm going to put 8 divided by 0.15 equals 53. Or let me, 8.6 divided by 15,000 equals 533. All right, so we see our gain's going to go down. Before I move on, any questions about that? Am I going too slow? All right, so let's go back to our sims. Let's go here to example 2. Let's go File, Save As, and go example 4. And then let's do a little stretching. And then go over here, and then grab this, pull this down, grab the resistor, right click, put this as 10K. And you know what, let's do real quick before I do this. Let's do a .op to see how much the operating point changes. Shouldn't change, but we'll see. View, Spice error log, GM. It didn't change too much, did it? GDS, they didn't change too much, right? Yeah, that's why you use a beta multiplier and you do things with constant current for biasing. And now I go back here, and I go back to transient, okay, hit save, hit run, hit V in, boom, add plot plane, hit V out, boom, and let's subtract out, how about minus 1.09? Too much. 1 point, yeah. I don't know what that means. I'm gonna shift it up. 6.
Add point zero.
No, I don't want to do it that way.
Oh, we're doing this now.
All right, I'll do it your way. There we go. How's that? Close enough. All right. So the gain is pretty close to what we calculated, 533. How can I tell that? Inputs 0.1 millivolt, outputs roughly 50 millivolts, a little bit less than 50 millivolts. Any questions? Have a good day. We'll see you on Wednesday.